we have some expression that we've solved for. Right, this is our general expression here. So this is the combination of the homogeneous and the particular solution, added them back together, and now we need to enforce boundary conditions to solve for these unknown constants. So let's do that boundary condition part. First of all, what are the boundary conditions? We have at the very left-hand side at x equals 0, right at this plane right over here. Let's just assume that we're given a temperature. It's called the base temperature. So BC1 T at x equals 0 is equal to TB. This is either a temperature that we'll solve for in some other way or a temperature that's given to us as part of the problem. The second boundary condition, BC2, is at the very end, on the right-hand side, we have an adiabatic condition. So this is just saying Q dot at x equals L equals 0, right? Which we know is going to end up being dt dx at x equals L is 0, right? Equivalent for this problem. Situations for extended surfaces where there's an adiabatic tip does not necessarily mean that there's like a symmetry condition or insulation. Sometimes it just means that the fin is long enough that there's no temperature difference at the end of the fin between the fin and the surroundings. So if that's the case, then there's no reason for heat to keep flowing, right? There's no heat to move. So it's not necessarily that there's, like I said, insulation or something else going on. It's often the case for like well-designed fins that the tip is effectively adiabatic. And you can just assume that, right? And it makes the modeling easier. Okay, so let's implement these. So boundary condition 1, we're saying TB is equal to, plug in T at x equals 0, that is C1 exponential of 0 plus C2 exponential of 0 plus T infinity. Right, so that yields, exponential of 0 is 1, so that yields TB is equal to C1 plus C2 plus T infinity. Right, that's our first equation from the boundary conditions. Second equation, BC2, Q dot at x equals L. Let's just skip to the dt dx part. So we're going to say d dx of Q dot. So, sorry, d dx of temperature, right, dt dx. So our temperature equation, again, is C1 exponential mx plus C2 exponential minus mx plus T infinity equals 0. Okay, so take the derivative of that stuff inside, and you're left with C1 times m times exponential mx minus C2 times m times exponential minus mx. The T infinity goes away. And then we have to evaluate this at x equals L, I guess. I'll put this up here. So all this stuff, let's evaluate this at x equals L. So I'm going to sub that out, right? So x here is L, x here is L. So I'm not going to rewrite that. That all is equal to 0. Okay, so two equations, two unknowns, right? C1 and C2. Nothing, there's no x's left over, anything like that. So we can solve, and we get, for this problem, C1 is equal to C2 times m times exponential of minus ml over m exponential of ml. And then combining that with the other equation for boundary condition 1, I guess that yields C1 is equal to TB minus T infinity exponential of minus ml divided by exponential of ml plus exponential of minus ml. All right, so we have two equations right here, this one and this one. Okay, so we have our constants, we have our general solution. You can just take these three equations, throw them into e's, and solve it if you give yourself an x value. Okay, questions on this process?
You said three equations, don't we only need two?
Three equations including the general solution. So you'd need general solution that computes temperature as a function of x. Then you have these two equations for the unknown constants.
Whenever you have something that's adiabatic, since there's no heat flow over it, does that mean the adiabatic place is always like one of the hottest or like equal to the max temperature?
Yeah, so the question was, if you have an adiabatic boundary, is it always the case that that boundary corresponds to like a minimum or maximum? It was a good question in temperature, and that's a good question. I hate to say it depends, but I think usually, yes, that's the case. Like, so if you have like generation occurring, or you know, like in this case, you have heat loss to the surroundings, I think it's usually a good assumption that it's going to be either the minimum or maximum, just because otherwise you're requiring like big swings in the temperature, like nonlinearity in the temperature, and it usually doesn't happen. So yeah, usually it is. Not always, but usually. Okay. Any other questions? Okay. Okay, so we have our system of equations. Let's go a little further. So for fins, this is like a really common problem dealing with fins. So people like to take the solutions that we just developed and put them in like a kind of more packaged format. This is the kind of thing like when you're doing analysis as a professional, you just come back and use this version that we'll get to. But I want to see or show you how we get to that. So let's take our expression. What I'm going to do is rewrite it, our general solution, sub in the unknown constants, and then do some normalization. So it's exactly the same thing we just derived, but it's just sort of rewritten. So we're going to write it like this. So let's say our temperature, which is a function of x, our temperature, we're going to normalize this temperature. So I'm going to say Tx minus T infinity over Tb minus T infinity. This is a normalized temperature, Kelvin over Kelvin. This is going to be a number between 0 and 1, right? Because T infinity is like the lowest sink temperature in the system. Tb is the hottest as far as the fin is concerned. So this is going to be a number between 0 and 1. In the numerator, we have exponential of this quantity minus ml times 1 minus x over L plus exponential of ml times 1 minus x over L. And then that's all divided by exponential of ml plus exponential of minus ml. M, okay, so what is this M thing? So M is part of this fin parameter, or fin coefficient. So for this problem, M equals the square root of perimeter times h bar over k times AC. So this is actually, it just comes directly out of the solution from before. If we look back up, yeah, so I was using M up here. M is just this coefficient of all the stuff that ends up multiplying. So in the fin problems, we have, you know, perimeter, the cross-sectional area, the heat transfer coefficient, the conductivity. For this problem, we assume just convection, right? So this M that I'm giving you is just for this problem. In the homework, as you'll see, I've added a little bit of more complexity. I guess I'm kind of mean. So you have convection to worry about, and you also have radiation. So you're going to have this M that somehow involves both convection and radiation. importantly for the homework while I'm talking about it, if you try to solve for this radiation part of it and you include temperature like as a variable, and then you go back, you're not going to be able to solve it. So what I told you in the problem is just to assume a T bar. Remember we talked about this radiation approximate formulation? Assume a T bar and just leave it, right? Don't update it at all. That will make the analysis possible. Otherwise, you're going to end up with T to the fourth, which is a nonlinear, non-homogeneous ODE, and you won't be able to solve it, right? Okay, so what I was saying, so M, this M coefficient, is going to show up over and over and over again, and so it's how we talk about fins, right? It's how we talk about fin performance. So M is per H over KAC, the square root of all of that, right? Numerator and denominator. And that shows up. So let's see, we have M. Some other things just to kind of simplify this down a little further. I'm sure all of you remember these hyperbolic trig functions. Actually, I'm sure you don't. So there's cosh, right? Cosh, sinh, tanch. Those are the ones we use for the most part. Cosecant H. I don't know how to say that one. These are basically alternate expressions that are they're just exponentials. So these are like useful functions that have been packaged up in these trigonometric names. They have properties like trig functions, like cosh of 0 is 1, sinh of 0 is 0. So it behaves kind of similarly, but they're actually different functions. So you remember if we take cosh of some argument a, that's equivalent to saying exponential of a plus exponential of minus a over 2. That's the definition of cosh. The definition of sinh, S-I-N-H, of some argument is exponential of a minus exponential of minus a over 2. And then tanch is just sinh over cosh. All right, so if you ever run into a situation where like you're doing a calculation, it calls for cosh or sinh, you can always just do it in exponentials. Or you can use the hyperbolic function on most scientific calculators to do that. Or just use e's and you don't have to worry about it. Okay, so that's the definition. So let's rewrite this in terms of sinh and cosh, because this is normally how it's done. So rewriting our normalized temperature, T minus T infinity over TB minus T infinity is equal to cosh of ML 1 minus X over L over cosh of ML. Right, that's just a slightly more compact way of writing this. Okay. One other thing, so this is like the compact way. So this is, if you wanted to predict fin temperature profile, this is the equation you'd go to. Adiabatic, constant cross-sectional area, convection only, this is what you'd go to. For the homework, you'll have to derive something kind of slightly different from this. So this is the expression. I want to point out right now that there's something kind of interesting about this M parameter. So normally we talk about M times L, right, this product here. We'll say this is the fin parameter. M times L is kind of special because it's this non-dimensional parameter that lets you describe what the fin is going to do. If we look at M times L, let's go to the next page here. We'll actually go back to the previous one in a second. But if we look at M times L, like I said, it's unitless. So M is 1 over meters, L is meters, it's unitless. This plot shows us the temperature profile as a function of position. So X over L from 0 to the tip of the fin. And then from temperature from 0 to 1, where 0 is like T infinity, 1 is like T base. So this is saying if you go through and for whatever the fin, adiabatic tip, constant cross-sectional area, whatever the fin is, you compute this ML parameter, which is just geometry and heat transfer coefficients. You're going to get this kind of characteristic. So you don't even need to go through the process of solving it. If you just know ML, you're going to know what to expect. So for example, if we look up here at this curve, this is a little hard to see. Let me flip the colors for a second. Squint your eyes. Okay, there you go. So ML of 0.1 is that line kind of hard to see at the top. So that is saying my fin parameter means it's a relatively short fin, right, in non-dimensional terms. So if you have like a really, really short fin, then basically the entire fin is at this base temperature. It doesn't have much time to drop in temperature, or much space to drop in temperature. On the other hand, if you look at ML equals 50, this is an extremely long fin relative to the heat that it's trying to reject. So basically you get this immediate drop to zero, ambient temperature, and almost all of the fin is just wasted metal or wasted material. So if you're designing a fin, normally you want to use the fin, use as much of the metal you're buying as possible. So you might be looking for MLs like in this range to make sure that it's. So you have the opportunity to do the design part of it on the homework as well. Let's leave it there. Question. Yeah.
When you mean dimensionless temperature, is that the current temperature over the surrounding temperature?
Yes, it's like the temperature at some position X. So it's that normalized by this other temperature difference. So let's leave the ML part there. I'm not going to go back there. Another note, it's not important. So let's just keep moving so you have enough to do your homework. Any other questions on this before we move on? Yeah. Yes, so the question was if ML is really small, adiabatic doesn't hold. Yes, unless you have some other means of preventing heat transfer from the tip, like insulation or symmetry or something, right? You can all imagine what I mean by symmetry. Like, so let's say you have some body here and some body here, and they're both at TB, and then you have this fin, and the fin extends across like this. At this boundary here, it's symmetric, so that's adiabatic, right? Heat's going to flow towards that, but there's no reason for it to go across that boundary.